I realized that I just told you floating point numbers were terrible. That seems inadequate. I think you have to experience how horrible they are, right? And I remember when I first started experiencing how horrible they were, that's what emboldened me to only use integers, right? And so I want to give you the same experience. So the plan for this week is we needed to do something while you have a little bit of extra time to work on SHA in case it's too hard, right? So I'm going to teach you something that there isn't a corresponding homework for, but there is code you can write if you're looking for something to do. And so today I'm going to teach you a little bit about the floating point numbers and the sort of design decisions and stuff that go into them. The lab on Wednesday is to implement the 16-bit floating point standard in Rust. The 16-bit floating point standard is supposed to be implemented in hardware, so it will be very slow if you introduce it implement it in Rust. But that's building us towards two things. I am going to ask you to do a lot more bit manipulation, and you will do bit manipulation to implement the floating point standard, and I'm also going to ask you to implement your own integer library once you see why the floating point library is so bad, right? Looking forward to that stuff. That stuff's all after the midterm. I haven't quite decided what to do for the midterm in this class. How many of you were in cryptographic systems last term? That's not very many hands. Do you think I could use the same midterm in this class and you just, like, don't tell anyone? Okay.
Probably.
Cool. Yeah, and it'll still be in Rust, so it'll be fundamentally different. Okay, because I liked those midterms a lot. I'd use them again. But, like, if it's only 3 of you are double dipping, that's fine. Okay, so I do know what the midterms are going to be in this class. I will get those ready pretty soon. And they're also so cool. I just feel like all of the things I teach are so cool. Do you ever feel this way?
Sometimes.
Sometimes? Okay. I was expecting a loud chorus of yeses. Or like maybe like a, oh yeah, like Kool-Aid person.
Kool-Aid Man.
Is it Kool-Aid Man? And Kool-Aid Man like goes through the wall and is like, oh yeah, right? That's a thing that happens? And Kool-Aid is made out of what? Calories, which apparently you consume 400 of per hour. Okay. This is a little low. Welcome to Systems in Rust. This is a lecture on numbers. I think, I don't know that I love numbers, but they're an interesting problem to think about because you get to sort of look at the interfaces between electrical engineering and mathematics that create the basis of computer science. And in this class where we're teaching a systems programming language, all of the design decisions that are made around this mathematics, electrical engineering interchange, all of those affect the things we do, right? So I think you've probably spent a few days getting really annoyed by how bits work, right? This lab today is going to do one of two things. Either you will get more annoyed, or if you were not previously annoyed, now you will get annoyed, right? Okay. So we're going to understand the basics of the floating point number. We're going to understand the language of floats, and language here I mean the sort of the operations and the nomenclature and things of this nature. I'm going to try and give you a sense of when you're teetering on the brink of oblivion while you're using your floating point numbers. And I'm going to try and give you some tricks to deal with that, and then I'll have you prepared to keep learning about IEEE floats. And the IEEE floats will be the subject of the lab. Does someone want to say what they think IEEE is? Okay, good.
Ieee.
IEEE is, I think it is the International Something of Electricity and Electric and Electronics Engineers. It's Institute of Electrical and Electronics Engineers. It is the international governing body of electrical engineers, right? The IEEE was just sort of like one of these guilds or professional societies for a while, and then someone put the electrical engineers in charge of making computers. And now they are basically the most powerful engineering organization in the world. They have pretty strong influence now over things like nuclear engineering and biomedical engineering, because biomedical engineering uses materials and sensors and imaging, and nuclear engineering uses computerized control systems. So the IEEE, basically, everything that works either works or it doesn't work because of IEEE. They are massively, ludicrously, hilariously politically powerful. They've sort of spent the last 8 years semi-regularly releasing diversity statements just to challenge the United States government to be mad at them, and like no one can actually do anything about it because every single traffic light would simultaneously stop working if you got mad at them, right? So I think they're just kind of like poking the bear for fun right now. They're in charge of things like semiconductor fabs, for example. So basically the only manufacturing that happens in the United States right now is semiconductor manufacturing, and there's some vehicles. The vehicles are now all electrical vehicles, which means they're also made by the IEEE, right? So, take that out, mechanical engineers. I'm not going to flip off mechanical engineers; they're nice, but like, imagine like, oh, right, okay. I'm not trying to start fights. Any physicists? I respect you. Okay. Okay. I'll do my one physics joke too. Right. Okay. So let's see. How do you do it? Right. Okay. So there's computer science, right? And then there's also computer engineering, which is the engineering form of computer science. But so, like, what is the science form of electrical engineering and mechanical engineering? So we need, like, electrical science and mechanical science. That's physics, right? The first two semesters are mechanics and then E&M, right? So physics is like the real version, right? Or the fake version, depending on who you're trying to annoy at any given time, right? So, yes, IEEE. Okay. So IEEE, they're this culturally and politically powerful organization. They're responsible for doing things like making semiconductors. Well, one of the things you're responsible for when making semiconductors is if big science, for example, if all those electrical scientists and mechanical scientists want to figure out how to simulate a nuclear reactor, they probably can't do that with integers, right? Why not? I don't know. I could do it with integers. What's wrong with them, right? So, in the early days of computing, by which I think I mean the 80s, but I might be lying. I tell lies sometimes. A few scientists were like, hey, these computers seem like they would be useful to do calculations, but I really want to put pi in one of them. And I, of course, would say, well, you can approximate that with 3. And then someone would say, like, isn't computer science not a real science? And we'd be like that, right? And so we can't do that. So someone made the electrical engineers put pi in the computer, right? And then someone else after that said, what if we put pi the same way in every computer? So that if I write some code over here that calculates if a bridge won't fall down, and then I email it across the ARPANET, because the internet didn't exist yet then, to my friend who's working at Caltech instead of MIT, they run the same code, the code gives the same answer. Because in fact, the same bridges fall down or don't fall down, regardless of where they're built, right? So a standard was introduced for how to write pi into a computer. That's the origin of the IEEE float, and it required the backing of this powerful political organization. I don't know how floats work. Not to worry. I found someone who also didn't know how floats worked, who gave a talk at the C++ conference in 2015 who explained how floats worked. And I just translated everything into Rust. Okay. So, on the good version of the slides, I fit this onto the screen, by the way. But here's our mission statement. We can imagine there's 2 use cases for floating point numbers. Every couple years, I teach CS1, and the students really, really want 5 divided by 2 to be 2.5. And I try to explain to them this is wrong. 5 divided by 2 is obviously 2, right? And they don't believe me, because so many times in their life they've had 5 of things, and they cut it in half, and they got about 2.5 on each side, right? And I try to explain to them that this is wrong. They don't believe me, right? And so they're like, can't it be 2.5 or 2.5? And I'm like, yes, but you have to use floating point numbers. And then the other example is, have any of you heard of the global financial crisis? That's good. Cherish that, right? So if, for example, you were trying to cause a global financial crisis, you would probably do a bunch of calculations like this to predict the sales prices of derivatives. And I think it's pretty obvious what's going on here, so I'm not going to try and describe it. Okay, I winked at the camera. I don't know how many of you were looking. And you can also like accelerate this on a GPU, and then it looks even more heinous. So anyways, this is the Black-Scholes equation. model, and it's a mathematical model for the dynamics of a financial market containing derivative investment instruments. And it's look. Does anyone know what a parabolic partial differential equation is? Yeah. So me neither. But apparently, if you know what those are, you have to use floating point numbers to model them. And I imagine one reason you have to use floating point numbers is, do you see this square root right here? Most square roots are not integers, which is why I simply avoid taking square roots, right? Remember last week when I made you take square roots without using the square root function, using binary search? You can't make bankers do that because they have money, right? You can only do that to students. As soon as you graduate, no one can make you do that. Here's another one. And this is a fraction over a square root. So this is, I'm going to speculate this thing might not be an integer, right? This expression might not be an integer. Here's a natural log of a fraction, probably not an integer. So a lot of people, they look at the floating point numbers and they're like, the good old-fashioned numbers that I know and love, the numbers I grew up with, the numbers that I use to do things like bake a cake, right? Everyone always wants to use a half cup of something. Not me, I only use integer numbers of cups, right? So I either use 0 or 1 cups of every ingredient. I started cooking in tablespoons. It's much easier, right? Because I get to measure my ingredients again, right? And so oftentimes people say, the floating point numbers, they're just like the numbers I know and love. That's not true. Floating point numbers are extremely degenerate, and they only happen to semi-regularly look like the numbers you know and love. But under the hood, it is complete madness and utter nonsense, right? Here is a more common thing with people that know a little bit more about floating point numbers, which is that anytime the solution to an equation, or anytime someone asks me to perform a mathematical operation and I get a number that doesn't look right, I can just blame it on floating point error. Fortunately, that's also not true because we can exactly predict where the errors will be in floating point calculations. Even though they are bad and evil and wrong, we know the exact manner in which they are bad and evil and wrong. And in this way, they are like Wile E. Coyote, right? They are not like Machiavelli, right? Which are the two forms of evil. Okay. Now, all of us voluntarily choose to use Windows because we believe it's the best operating system. And the reason we do that is because we believe Windows handles floating point values differently than Linux. That is not true either. Floating points are handled by the hardware in your device, more or less. I found some exceptions, and I did not find them where I expected to find them. But it seems like sometimes programming languages use them differently, so I guess you might think that you're getting different results on Linux and Windows if you have different versions of a programming language, for example. Specifically, the corner case I found a different result when using Julia in Python, and that was very surprising to me because I thought Julia was intended as a replacement for Python that was more stable. And then lastly, floating point represents an interval value near the actual value. This is also not true, but it is a little bit true. There is such thing as interval algebra, where you say, for example, I have a number in the range 1.1 to 1.3. And I am going to multiply it by a number in the range 0.5 to 0.6. I lost a significant figure, so I gained 1 degree of precision, right? These are both about 20% approximate, right? Well, if I multiply these together, I know the solution will be between why did I write 6? I was even going to say 5.5. Well, okay, I'm going to find the eraser. If I multiply something in this range times something in that range, the answer will be something in this range. Does that make sense as a method for approximation? Did I do this right? 1.3 times 6.
Wouldn't the 0.5 and 0.6 reduce value? Okay, that makes more sense.
And I think we can just... Is this okay? Is that okay then? So, one way to do approximate values is to say, I I know a number that is larger and a number that is smaller and a number that is larger of my two things. I'm going to multiply them all together, and I will get back an interval. This is not quite what floating point does. It makes much more sense to think of this as, so imagine we're trying to approximate like 1.247. Floating point will instead say, hey, you have to pick something. I can either store this as 1.246 or as 1.249. But you get to pick which approximation you use. So you are dealing with approximations, but they are not intervals and they do not have bounded error. There are such things as interval libraries. They're much more expensive. Here's another common fallacy, and I think you will begin experiencing this fallacy right up until the moment, beginning from when I teach you how floating points work and continuing up until I ask you to implement floating point yourself. A floating point double holds up to 15 decimal places that are basically can be assumed to be correct of numerical values. And so often it is the case that someone says, oh, I have 15 decimal places, and I need to store 1/5. I should be able to store that correctly. And sometimes that's true, and sometimes that's not, because it actually is dealt with the internal machine representation, and it comes down to whether you can express that value in binary without any trailing ones, which is, at least to me, highly non-intuitive, right? Another common fallacy is my programming language does better math than your programming language. This is only true if your programming language is Haskell, and otherwise it is false. And I have an example later in the slides of when you use Haskell instead of other programming languages for this. And then the last thing that, and this is a more common CS151 question than a CS271 question, is why do we have to learn all of this? Why can't the computers just use numbers? And the reason for that is because of how many numbers there are. So just think about this really quick. Like, what is the largest number you can think of? Okay. And is that more or fewer than the size of your hard drive? Well, you can think of the size of your hard drive, so by construction you can think of a number you can store in there, right? Because all you have to do is raise 2 to the power of the size of your hard drive and add 1 to it. And you can think of that operation, and your computer cannot, right? So fundamentally, we cannot just use numbers because there are infinity numbers and there are not infinity computers.
Also, if you're going based off of hard drive, then that would assume then I guess you're using swap in that case.
I don't know what you're using. I think you're using your brain. The IEEE float specification apparently came out in 1985. Something happened in 1987. And in 2008, something else came out. The thing that happened in 2008, I believe, is I'm going to ask you to implement Float 16 for the lab. And Float 16 was a non-standard format, so it was added in 2008. And I believe the reason it was added in 2008 is for machine learning acceleration, but that doesn't make sense because machine learning wasn't a big thing in 2008. So I don't know why it was added in 2008. It doesn't make sense to me because it is used now. It's used all the time. Floats became much more popular for ML. Essentially, everyone was using ints when I got really into using ints, and they don't anymore. The GPUs use floats. I was just going to give you links to these things, and they're paywalled, so you can't actually see them. Of course, you can find them using the normal methods, but then they might be out of date or something, right? The goal of IEEE 754 was to make results consistent. It was not to make results correct. There was not a premium placed on correctness. They didn't want things to be expressly wrong, but the goal was for them to be the exact same way every time. So we have a different goal than we commonly do when doing mathematics. Okay. There are some assurances that the floating point standard provides. It provides for symmetry of addition. X plus y will equals y plus x. It has very strong guarantees around 0, which I think of as the additive identity. So anything, if you add the additive identity to it, you get back the same value. And if you multiply by 0, usually you will get 0, but not always, right? And then it also has identity under subtraction. So if you subtract x from itself, you will get back 0 in all cases. There are some slightly more sophisticated assurances, and this is the one example I know of, which is if you take x and you divide it by the square root of the square of x plus the square of any other value, this will be less than 1. So this gives us a bunch of inequalities. For example, this forces y squared to always be greater than 0, which means we do not have imaginary numbers. There are no imaginary numbers in IEEE floats. It requires us to make sure that we are rounding down in certain cases, because if I throw 0 in here, I could introduce error when I square in square root, because 0 is a valid number. And so getting that assurance there is pretty important as well. This basically means that square root must precisely reduce squaring. You might notice some things are missing. Here's an example of something that I did not guarantee. I did not guarantee that x plus y plus z, if I put parens around the x, is equal, I'm going to just do triple equals equivalence, to x plus y plus z. This is not guaranteed, and in fact there are counterexamples to this. And so there are other things that floating point numbers do not do that you would expect numbers to do. So, what do we have to do? We have to ensure every floating point number is unique. This is the same problem as hash collisions. We want to make sure that there is a bit representation of every floating point value that can be differentiated from every other floating point value. So we want to make sure that we don't somehow say like negative 1.1 and 1.1 have the same representation or something like that. But it can be the case this is allowed. It might be the case that 1.1 and 1.1 15 zeros 1 have the same representation, because these are not distinct floating point numbers, they are distinct real numbers. And I'm dealing with a subset of the real numbers. So this is allowed. I have to specify these are elements of the reals. The floating point numbers are much, much closer to being rational numbers than they are to being real numbers. Every floating point number must have an opposite. Let me give you an example you probably don't necessarily expect. 0 is a floating point number. We almost always stylize it as 0.0. Because every floating point number must have an opposite, there exists negative 0.0 as required by the floating point standard. I hear the sound of you not believing me. Don't worry, I'm going to demonstrate. What's everyone's favorite programming language that isn't Rust? Or Haskell? Or Go?
JavaScript.
Assembly.
I don't think assembly is I don't think either of those are programming languages. JavaScript's a scripting language, and assembly is a hardware specification language. So it must be Python. Whew, that was a close one. If one of you had said like an actual language, I'd be in big trouble. Like if you hit me with C++, I was going to have to learn C++ in front of all of us right now. Okay, so there is not 0 or negative 0 integer, but I believe there is negative 0 float. Easy. Isn't that kind of weird? What if you subtract 0.0 from 0? So I would expect that to be negative, but I don't know, right? How do you get to this? Well, usually you start with something that is very small. And you make that negative. And then I think you just divide a bunch of times. Oh, it's not getting, I have to say x divide equals. There we go. So at some point this might go down to negative 0. I don't know how long this takes. Why is it representing it differently each time? Okay, so remember when I was like, these are fake? That's just wrong, right? Where did this? Okay, I'm fine. This isn't quite fast enough, is it?
Oh, it's going to 2D now.
Wow, this is getting really tiny, huh? There it is. -0. I got it by simply dividing a number by a large number many times. I would like to point out this is supposed to be a okay, like these numbers are super fake, right? Like where did that okay, I'm fine. Okay. We define algorithms that describe addition, subtraction, multiplication, division, and square root. It is not the case that we should necessarily say that these are the mathematical idea of a function. They differ from functions in a few ways, namely they are not bijections. That we can sometimes multiply x by y and x by z, y and z not equal each other, but the product equal each other. So just look out for that. And I think that happens when we say, like, hey, I have x equals 10, y equals, how many zeros should I put here? I lost count. And then z equals 1. Let's make x bigger. 30. Okay, so we have x, y, and z. Z has to be a float. So x times y, x times z. These are different values. Maybe they're not counted as equal. Okay. So let's get a slightly bigger z, y. What happens if I do f quote, does anyone remember format strings? It's like this.
It needs to be a double quotation mark.
Wait, for, for format strings? Okay, so what we really need to do is we need to get a y that doesn't round down. There we go, got it. Okay, so that, we have z, y equals z, not true, x times y, x times z. Ooh, they are different. Can we make a smaller y? We're losing it. Is that smaller than this? Yes, right, because those are 1s, so that's a 10th. I don't think I can get it right now. You would expect those to be more different. Let's make x bigger. Like 70. Now it's able to retain it. Okay. I'm not clever enough to do that right now. At some point you should lose precision. Where should you lose precision? Usually when you run out of digits, basically. Right? So these things are all about 15 bits of precision. Or 15 digits, right? So that's probably around 15 digits. Okay. Scientific notation. You'll know what scientific notation is? Okay. Okay, IEEE layout. I'm actually going to write this on the board because I started writing on the board earlier and it felt nice to me, so I'm going to continue doing that. Did I ever start recording? That was close. Okay. When I was taking my undergraduate classes on basically this class, it was explained to me, and I don't know if I believe this, that the floating point numbers were not designed by people that understood how computers worked, but they were designed by people that understood how scientists wrote numbers down. It almost feels in a way similar to a string format. And so let's write this down. We represent a value x as having some numerical sign, either plus or minus, which we represent as -1 to the power of a sign bit. I'm just going to write sign bit here. Why is that? Because the first thing you see when you look at the scientific notation representation of a number is whether it's positive or negative, right? The thing that comes after that is the power. Now, the people that did make this, who have been accused by some people of not understanding computers, did in fact correctly intuit that you should be using powers of 2. So we do not have classical scientific notation with a power of 10. We have a power of 2. And you raise this to some exponent. Notice that I'm not saying exponent sign. That is a field. That is going to be a bit string. It is going to have some length. We'll decide the length later. And we're going to multiply this, again, by 1 point something. This got really weird for me. I thought this was quite strange. I don't know why you do 1 every time. This is not quite classical scientific notation, right? Because I think classical scientific notation, you ranged from 1 to 10. Did I make that up? This is ranging from 1 to 2. So if I put all zeros here, then I get 1. And if I put 9s repeating there, then I get 2. Okay, and why is that? Well, we range from 1 to 2 because we're using powers of 2. So instead of ranging from 1 to 9.9, as in scientific notation, we range from 1 to 2. So there is something here, and it is called, at some points in time, the mantissa. I don't know what that word means. Jimmy Osler told me we're not supposed to say mantissa anymore, so probably this is not actually a mantissa. It's probably something else. So if you're looking for something to do, find Jimmy and bother him, okay? And that would be a personal favor to me because, well, you're bothering Jimmy, Jimmy's not bothering me, and then the class is better, right? So this is the attention economy, right? Okay, so somehow we have to put this inside of a computer, and so we do that by representing it in binary. So we take, for example, a binary value. And I'm saying represented as binary. It's just information, right? It's just information. So maybe we have a 16-bit floating point value. Perhaps it is negative, so the first number is -1. In Rust, I am permitted to put underscores inside of numbers, so I'm going to use that notation here as well. I believe in the 16-bit floating point specification, you get 5 bits for your exponent. So we can say, we'll raise something times 2 to the 10th, right? So in binary, that is 0, 1, 0, 1, 0. Is that 10? Decimal 10? It horrifies me that you're all just looking at me. Should I be afraid right now? Are you all having fun yet? Okay, all right. And then let's imagine the number we're trying to represent is, does anyone have a favorite number between 1,000 and 2,000? Well, obviously, we should use 1985 because that's the year of the floating point standard, right? Okay. So, in order to figure out what the mantissa is, I would divide this by 1024, which is really just 2 to the 0b 1010. I'm going to use my fourth favorite programming language to do that calculation. Okay. And so I have, what do I have? I have 93876, I don't know, right? And I'm going to represent that in my remaining bits. I said this is a 16-bit, which means I have 10 bits left here, which means what I should be doing is I should figure out what I can store in 10 bits, that's just 2 to the 10th, which I already did, right? Did I make that up? Okay. So I need to subtract 1 from this thing and divide that by 1024. No, I multiply that times 1024. And then I need to express that in binary. Is it 4 ones? And then 5 ones, then a 0? Well, how many zeros?
5 zeros and then a 1.
5 zeros and a 1. That's what I tried to say, and I just didn't say it. Okay. You would think in bits where they're either 0 or 1, I would be able to correctly describe what digit it is, but in fact I have a 50% error rate. But this means if I were using decimal, I would have a much higher error rate, right? Okay. So I believe this is the binary representation of the decimal value 1985 in a 16-bit float. But do I know? Not really. That's just what I think. 32 bits and 64 bits are the standards. In fact, a piece of hardware cannot claim to implement a floating point standard unless it implements the 64 or 32-bit standard. So if you only implement a 16-bit standard, you are not floating point compliant. It is considered an extension to the standard that you can offer optionally. The 32-bit standard has 1 sign bit, 8 exponent bits, and 23 mantissa bits, and the 64-bit standard has 12 exponent bits and 52 mantissa bits. I think we should probably reverse some of this process. So let's say, I think I was trying to store 1985, right? So what I should say is 1.0 plus 961 divided by 1024. And I put that in parens. And I raise that to the power of 2. No, I multiply that times 2 to the power of 10. And that gives me back 1985. So we went through the process, and it is in fact reversible. Does this make any sense at all to any of you? Okay. You're all so smart. Okay. Okay, I'm gonna say one thing that I shouldn't say. Okay. So I teach CS1 and then a college colloquium, right? So I teach 2 hours of people that have never programmed before. And the whole time I'm thinking about how I can't wait to get to this class. Anyways, don't tell them that. Because if they don't take those classes, then they'll never be in this class, right? It's like an eat your vegetables angle. Like, this is dessert for me. You are all dessert. And so if I ever refer to you as like, oh, you're so sweet, no, I'm thinking about food. Okay, I'm not thinking about your behavior. Okay, what is the probability a real number, A, element of the reals, has an exact float representation? Okay, I'm thinking of a real number. What are the odds that I can represent it as a float?
Small.
Exactly 0. There are infinity reals and finite floating points, which means if you randomly select one, it does not have representation. In infinity to 1 odds, basically, right? Oh, we can actually divide 1 by infinity and see what happens using the power of floating point arithmetic. Okay, so, I can't put in infinity. Not to worry, I'm a genius. Okay, from NumPy, import inf as inf. Wait, why didn't I just say import inf? Does my brain not work? That's the probability, okay? Are we allowed to use floating point to represent the probability of floating point being projected into the reals? I don't know. Go ask a math professor. Okay. What is the probability an integer, an element of the z's, has an exact float representation?
0.
How many integers are there?
Infinite.
How many floating point numbers are there?
Not infinite.
Exactly. There's either 2 to the 64 or 2 to the 32, right? What is the probability that a course number, and at Willamette University the course numbers range from, I believe, 0 to 600. In exclusive, they don't include 600, I don't think. What is the probability that a course number has an exact float representation?
100.
100. Because numbers close to 1 have representation. So when people say the floats feel like the real numbers, what they're doing is they're just not picking annoying enough numbers, right? They're picking numbers of things they've seen. So like you've never gone to the grocery store and seen pie bags of chips, right? And you've probably also never seen Googleplex bags of chips. And you've certainly never seen pi to the power of Googleplex, right? No one has ever seen that number, right? So people are like, oh, the real numbers I see all the time. I was like, no, those are the fake numbers, right? Those are the physical numbers that exist in the real world. Those aren't numbers. Real numbers are the fakest thing you've ever seen, right? Okay. Done with rant about real numbers. Okay. There are some special numbers in the floating points. Let's represent this. One of my favorite things to do with Python is pretend it's not Python, and I often do that by trying to turn it into Rust. So from NumPy, I'm going to import float32 as f32, and then I can just turn things into float32s. Look at this. Oh, it's delicious. It's beautiful, right? What's the type of that? Oh, I sure hope it's not a Python float. Oh, it's a float32. Oh, it's great. It's basically the Rust type, right? And I know that's the Rust type because it's implemented by hardware according to an IEEE standard, so it does not change which programming language I'm in. How do we get not a number? Well, usually you divide things by 0. So we can divide 1 by 0, I think. Does this seem like something that should be allowed?
I think it should error.
F32. Wow, typing is owning me. So you would think that is an error, right? But that's actually defined. So I'm getting a warning. But floating point arithmetic, which Python adheres to, is required by law to give me an answer back for this. So it's giving me infinity. How do I get nan? I probably divide like infinity by... Ooh, that's interesting. Wait, what should I don't know.
0 divided by infinity?
It would just be 0, wouldn't it?
Well, what's 0 divided by 0? That's the obvious thing to check, right? There we go. It's not a number. But it has to pass back nan. What's the type of that? I'm so glad you asked. I love it when you ask me what type things are. It's a NumPy float32. And by NumPy, they mean Rust, right? Because we're pretending we're Rust, okay? Now, that's not always allowed. And I actually don't know what happens if we do this. So Python is perhaps not as... Okay, Python doesn't have floating point numbers in it. What Python has is the float class, and the float class uses floating point numbers. But it does not actually do floating point arithmetic, because floating point arithmetic requires you to give someone an answer back when they do this. And Python doesn't. It's still the same x. Oh, wait, I should del x. So, this is not allowed. A compliant floating point implementation would require some value to be placed in x there. And the value can simply be not a number if it's not a number. And so we see this when we F32 everything first. So I realized, so on the lab, I'm going to ask you to do F16. F16 is the name of a plane, right? So my brain was getting destroyed the whole time, because if you're doing aerospace, if you're modeling a rocket or something, you can use floating point for that. If you're deciding roughly how many grams of fuel to use, things of that nature, that makes sense, right? But if you're running code on an airplane, that absolutely cannot be a floating point value, because you can never get not a number back, right? Be like, oh, hold on, I just need to calculate if I have enough fuel to get to the next airport. Oh, the solution is not a number. So I was my brain was being destroyed the whole time because I accidentally kept thinking about aerospace, and that's not allowed. Okay, I just thought, it's important to talk about your feelings, right? Okay, so we have signed infinity for overflow protection. F32 of 10 to the power of F32, 1,000. That's fine. That's a very large number. If I do, does anyone know how exponents work? Is that going to be a negative number? Because it's an odd numbered exponent of a negative. Yeah? Negative infinity. Very cool. Thank you for helping me with the numbers today. And I think if you try and do this in Python, it tells you to like go kick rocks. 0.0. Yeah. So by the way, Python, hey Python, you in there? Python, you have to give me a number back when I give you a floating point. Okay. You can't just give up. You have to give me infinity if it's very large, right? Now I understand this number is less than infinity, right? Because I can count, right? But you have to pretend it's infinity because you, Python, or more properly you, IEEE 754, cannot conceive of numbers that big. So when the numbers get that big, you just say, I don't know, maybe it's infinity. So floating point infinity is actually a finite number, but we treat it as if it is an infinite number once numbers get that big. So we overflow, we say, hey, you're infinity now, and then we treat it like it's infinity. That's overflow protection. You can get negative infinity, which I showed you already. I tried doing this in Julia, and Julia got really sketchy, which I didn't like that much. Sine 0. I liked the sine 0 example. Did you all like the sine 0 example? Did you have fun during that? Never mind. I actually don't. I don't want to ask if you have fun because I don't need external forms of validation. I already feel validated myself. Okay. Floating point is great. I want to read this exact quote. Floating point is great because it will work exactly how you expect. Okay. So big, why can't we just work with numbers wants you to believe that this is true. It's not my fault that's not true, right? If I designed the numbers, you would have to express this differently. And how would you have to express this? You would have to express this as, does 1 plus 2 equal 3? And then if you really want to, you can divide both sides of that by 10. And that's completely reasonable, right? Did that divided
That's
true by
divided
10, right?
by 10.
That's true divided by 10, right? I don't know how to feel right now, but I don't feel good. Anyways, here's 0.1, here's 0.2, here's 0.3. You would think those are equal, right? Here's 0.1 plus 0.2. Oh! Oh! Oh, I don't like that very much. And what is the lesson here?
Don't use floating.
Don't use floating point, right? This is how I printed them out. But, well, actually, this is probably interesting to see. So I'm using just the format prints, and I'm asking for 100 digits. And you'll see they're clipping pretty early to claim this is 0.1, 0.2, and 0.3, right? Like there's a lot of signal to noise ratio right there, right? These things are very different. And this also gives me a hint. Let's see. X equals 0.1, right? And then I say F32 of X. I want X to be an F32. Okay. So here's X, and I want to print that as X get 100 digits. Okay. Right? And it's not giving me 100 digits because it runs out of digits, right? But this would suggest that if I take Y and I set it equal to like this much, what am I doing? Control-Shift-C maybe? Y equals... does X equal Y? No? Oh, what if I floating point 32? Y. Okay, that's pretty suspicious, right? Let's do, what am I trying to do? Okay. So if I F32 of this, and then I look at Y, or perhaps I F Y, is that right? I would think 0.1 and 0.1000149 would be different numbers. This also raises the question of like how large we can go here. So if I do that much, I still get the same value, right? But yeah, how high can I go? 8? Yeah, there you go. So at some point you start increasing the most significant digit. But it's worth noting that this value and this value, the second value is supposed to be twice as far away from point 1, and it is 6 times further away from point 1. Right? So that is a massive introduction of error range. I got a C6. So that's pretty weird. Okay, so here's an even better one. This value is 50% further away from point 1 than this value. But the difference is still 6 times harder. So a 50% change turns into a 6x change relative to point 1. That's bad. Okay. I'm going to go over how to store 1, and it looks like I had a parenthesis in here, but that's not too bad. I think that's manageable. So let's store 1 in floating point, and we have our notes here on the board, so we can figure this out pretty quickly. Okay. So I have, I'm going up to 32-bit floating point now, but we don't need to worry about the size yet. Okay. So I'm going to have a sign bit of 0, because 1 is positive. I'm going to have an exponent of 0, because 2 to the 0 is 1, and I'm going to multiply by 1. So I'm going to have many zeros here. And then I'm also going to have a mantissa of all zeros, because I am 0 more than the closest value of 1. So there are also many zeros here. What this should suggest to you is that actually quite helpfully, 1, regardless of the precision of the floating point type, is represented as all zeros, right? That would be extremely convenient if it were true, and it's not. Let's go ahead and get this working. Cargo, new, FP, CDFP, NVIM, circmain. What do I want to put in here? Okay, so I want to take a floating point value, which is going to be an F32. I'm going to set it equal to 1.0. I think there's a few other ways to do this, by the way. I specified the type of the variable. You can also specify the type of the value by suffixing with underscore F32, the name of the value. What am I going to do? I am going to print the line, and I am going to use binary representation. I'm going to ask for 0 prefixed, I need colon to do representation, 0 prefixed, 32 bits of precision, binary. Sorry, this is 32 digits of precision. I can say bits because I'm using binary. If I put an X here, it would still be 32 digits of precision. They'd just be hexadecimal digits. So I'm going to get 32 digits of precision in the binary format. And that's the way I'm going to print a value. What value am I going to show? I'm going to look at the bit representation of the floating point value. And there's a bunch of ones in there. Specifically, we can look at this and we can see, okay, the sign bit is still 0. The leading bit of the exponent is 0. And then there's a bunch of ones. My understanding is that in float 32, this is, I think, 7 ones, which means that this is, and I will prove it, Python 3C print 0b 1 2 3 4 5 6 7. This is going to be 128.7. I said 128. I meant to say 127. So I lied. And actually, I think more properly the floating point standard lies, but you shouldn't trust any of us anyway. I need to time check. Oh, sorry, I was having so much fun. I forgot this class had finite time. You know?
Like half an hour-ish.
Oh, that's not nearly enough time to talk about numbers, right? How many of you like this more than the class on SHA? Okay. How many of you like this less than the class on SHA? Really? Okay, cool. I had a lot of fun thinking about this, but I don't know if my brain works, right? It's like you should never trust yourself. Okay. Here's the deal. I didn't actually lie. And the manner in which I didn't actually lie is I didn't tell you what binary format I was going to use to represent my numbers. And the format I'm going to use for F32 is Shift 127 format, where I can represent positive or negative values by writing the number in binary and shifting it by 127, decimal 127. So I would represent negative 128 as 8 zeros. And I would represent positive, is that negative 128? I think this is negative 128. I don't know, right? I would represent 0 as this much. I don't have positive and negative 0 for my exponent value. That's only for the floating point values. And then I would represent 127 as this much. And I'll do underscores here so we can see it. So I set the 127th digit, or maybe that's the 128th digit. I don't know, it's kind of hard to think about all this binary. But basically, I have numbers in this range. I need 0 to be in the middle, but I can't use a sign bit. So I just subtract 127 from all of them. I think we can all agree that makes perfect sense. Okay. There's one other special thing going on, which is that, oh right, I'm off by 1. This needs to be 0, and this needs to be 1. If the exponent is set to all zeros or all ones, those are special values, and those are special values for storing positive and negative infinity, not a number, and some other special classes of numbers that I couldn't figure out, but they're called denormalized numbers, and they seem very confusing. So, something that you should have asked mentally when I wrote this up here is, well, if you have a sign bit, an exponent bit, and a mantissa, how do you store infinity? And the answer is, by convention, we disallow the exponent bit to be all zeros or all ones, and we use all zeros and all ones to store special values. So, let's take a look at how precise we can get by specifying. I'm going to take this value. I am going to put the 127 here. But I'm going to try and put a 1 in the least significant bit. So how am I going to do this? Well, I'm going to exit full screen. Okay. So I have some floating point value. Let's extract the bits from the floating point value. So let's say let b equal x dot 2 bits. And we can then print b. We run that. What am I doing wrong? I missed a semicolon. See, it's this changing programming languages thing, right? I'm back to doing :x instead of capital ZZ because it feels better on my hands and I'm tired of being judged. Okay, are you all using double Z or :x?
:x.
You're using :x. Is anyone using double Z?
I do, but that's because
You do?
what I was taught.
Because that's what you were taught. Maybe it's just the first one you use? Did you ever use double Z and switch over? Or no, you just started. Okay. Well, we'll never know. Okay, so there's my binary representation. What I want to do here is I want to set the lowest order bit of B to be 1. And usually I would do that with a bitwise operation. So I'm going to say or equal. I'm going to take a bitwise OR, and I could do it with binary 1, but I'm just going to say 1 because it's the same. If I do this, this is not allowed because I need to make B mutable because I'm modifying its value. So we mutate it. That's now allowed. We're not looking at it, so what are we going to do? We're going to grab that line. We're going to print it again. Now we can see we've added the 1 there. Okay, and then all we have to do is we have to transmit this back to F32, which I'm guessing you can do something like, can I do this? From bits B. Is that going to work? Wow, okay, I just randomly guessed something to type into Rust and it worked. Okay, so to narrate a little bit, this looks like a lot of zeros to me, and this doesn't look like that many zeros to me. But these are binary representation zeros, right? These are bits, and these are digits, and the D in digits in this point in time is standing for decimal. So I guess we should call hexadecimal digits either hits or higits, and neither of those seem like things you should say. So I guess we have to call them like hexits or something. I'm going to try and start using hexits unironically, and we'll see what happens. Okay. Wait, no, I want to do this. Oh, no, I want to do 0b. Okay. And I want to divide that by something like that still seems way too small, right? Oh no, because this is also supposed to be binary. Okay, so that's about 10 to the negative 7th, and there's 6 zeros here. So that seems pretty mathematically close to me, right? Does that make sense as an approximation? I took the binary representation, I conducted just a naive division, and I got something back that was pretty close. And I think that's probably true if I take, that's 6 zeros, right? So these numbers are close to each other. We would expect there to be a bit of a difference because we're doing like approximations and stuff. Okay. Cool. So here's the representation I found. Let's print more digits. Println. How am I going to get a bunch of digits out of this? I'm going to say 0.100. I don't know. Let's cargo run. Okay, and we can see that there's a lot of useless zeros here at the end, but we do have this value. So this is not exactly 1.01, but it is quite close. So this is actually a noteworthy value to us. This much is machine epsilon. Machine epsilon, why are there 2 of them? That's crazy. I think we've seen duplicated LaTeX on slides before, right?
I think they're different.
They're definitely different characters, but they might just be different sizes. View selection source. It's MathJax. Oh, there's so much text. %s/epsilon. Is it not in here anywhere? Okay. Oh, there it is. Well, there's one. I don't know what that is. So that's a Unicode epsilon. There's another Unicode epsilon right here. I don't know what's happening.
What do you use to write this?
Quarto, which is terrible.
What?
Yeah.
You mean you don't just raw type all your HTML?
So it is true I do that for some of my classes, but it's like a guilty pleasure. Like, you should not do that. Do not just type HTML. I've done it for years. It's awesome. You can do whatever you want, right? Like, the degree of freedom HTML actually gives you is like, it's clear how undefined the standard is if you start writing it for 5 minutes. It's amazing. Okay. The thing I really want to write is I want to write, So these are like slides, right, that use Reveal.js. I don't want to use a JavaScript framework someone else wrote for my slides. And what I actually want to do is I want to write, this is unhinged, but I have to tell you. I want to write my slides as JSON, save the JSON as an object in a script element of an HTML file, and then have it live render based on keystrokes. And so just build, basically display HTML inside an HTML body element by reading JSON. And it just changes what JSON it reads when I do that. But I've heard that that is inefficient. So instead I'm using something else. Anyways, okay, machine epsilon. I think of it as being named after the epsilon and the epsilon delta proofs, which is something that you make arbitrarily small, right? If you make something arbitrarily small on a computer, machine epsilon is as small as it can get. It's the distance between, I'm going to say distance, I wrote difference on these slides, but it is the difference between 1.0 and the next available floating point number. And it is different in different precisions. So if I change this to an F64 and this to an F64, I'll probably get different values. I guess we'll change these to 64 too. This should have just been a replace operation, but we're here now. So, dramatically higher precision with 64-bit, right? As we would expect. We would expect the precision to be twice as high, and it is. This table is very useful to me. This is from Professor Kahan, who's at, if I say UCB, does that mean anything to you?
UC Berkeley.
Yeah, UC Berkeley. EECS, what's that mean? Electrical Engineering Computer Science. So UCB EECS is a powerful organization, right? They are important for running the only Unix distribution that's not Linux, right? FreeBSD. So this table is useful to us. Only these two middle columns are standards, right? The other ones are extensions. And these correspond roughly to the number of significant figures we have. What do you mean by that? That is a 7 or 8 significant figure value. I don't know how sig figs work, right? But this 1 is significant. It is a 1. The 1 follows 6 zeros, and it is after a 1, so that is a 6 to 7 significant figure digit, as we say 6 to 9. Oh, what's this one? That is a 2. I don't know how many digits this is. That's 16 digits, so I'm going to say we have around 17 digits of significance. Same there. You will play around with half precision, and you'll see that it has around 3 to 4. I think the thing I specifically noticed is if I stored 123, I think it stored it as 124. So it got the 12 right. Oh, yeah, you might want to read this person's lecture notes if you're like looking for something to do. They're very nice lecture notes. But they're made in LaTeX instead of Quarto, so they're actually good. But I can make cooler looking graphics than this, right? But like, look at this. If I tried to put that on my slides, it would just not fit left to right. Here we got a table. Okay, sorry, we don't have to look at someone else's typesetting. But typesetting is cool and fun. I taught my CC students Markdown today, and they really liked it. So be thankful for what you have, right? Blah, blah, blah. We have sig figs because it's meant for scientific computing. That's why. That's all. I suspect this was like people were still annoyed how much manual mathematics they had to do during the Manhattan Project. Yeah, there's duplication going on here again. That's duplicated for sure. Right? Because this is... Why is that duplicating? Do I have a different web browser? Does anyone have these slides open on their own computer? We're on slide 35. I want to know if you have 2 of these or not. If you type in this URL, you'll get it. Open Discord. Has anyone found it yet?
I only see it on
You want to see it once? Can I physically look at your computer? Thank you. Yeah, okay. Cool, thank you. I don't know what's causing that. It doesn't seem to happen every time. I think it's loading a backup. Oh yeah, because it was double epsilon. Do you have any other LaTeX in here? None of these are duplicated, are they? Oh no, they totally are. Right, that's duplicate. That looks so bad. Okay, I'm fascinated by this. Okay, sig figs, small values. Okay. How do we represent 1.0 times 10 to the negative 37? Let's take this and let's throw it in there and see what happens. Or it's going to be easier to just copy paste this. So we'll copy paste this and we'll narrate. Okay. nvim circ main. No, not what I meant to do. Okay. So I just manually calculated this. It's a magic number, but it's a magic number that you determined by calculating, right? I'm going to print out the 32-bit representation. I'm going to print out with many digits of precision the F32 representation. I'm separately going to take 10. This is 10.0 as a floating point 32 value. And I expressed the type on both sides. You don't have to do that. I'm just doing that for redundancy. I'm going to raise it to the power, and I'm going to use float power. So this is a built-in Rust operation for float power. This is a float, so I use float power. And I'm going to raise it to the negative 38th power. So that's 10 to the negative 38, just 1 to the negative 37. Or 0.1 times, right? And that I have a 32-bit value, or a 32-bit floating point value. I'm going to print the 32-bit representation, and I'm going to print the first 100 digits. Okay. And we can see these values are the same. This is approximately, presumably that's, can I do this? Oh, I added a bunch of extra characters there. Does anyone who knows how, wait. Is it echo? I'm going to try and measure this with pipes. Okay, so that's 39 zeros, which makes sense because we were doing to the negative 38th, right? And I just destroyed my brain trying to do that. But what I did, because this is a 9, so it actually should be one less, right? Because that almost rounded up. Okay, so I took this, I copied it into my paste buffer on my operating system, which is provided by my operating system. If you don't have your operating system doing that, you have to pipe this whole input, right? I echoed that so I could see the value. Then I added a pipe, such as to cat, which would just show it back to me, or to printf or something, anything that just shows it. Oh, do I have to do echo? Okay. And I wanted to count the number of words, so I used word count. So I did echo pipe to word count. And that is the same thing as treating this as being the contents of a file, which I word count, and you can demonstrate that by applying word count to a file, and you see a count. This is, one of these is lines. I think it's like paragraphs, lines, characters, so there's 39 characters here.
I assume paragraphs is probably based on annual line rates.
I don't know. New line, word, and byte. Oh, no, it's words.
Okay.
So this has, that's counting spaces, I guess. I don't know. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's about the number of spaces. I don't know how it's counting it. Okay. There are also denormalized numbers. These are numbers with the 0 exponent. So that's, we have to put a 1 here. So if there's actually all zeros here, this is denormalized. Denormalized numbers are intended to prevent underflow. I don't know a stable way to interact with them in Rust. There's a C++ standard library to deal with them. I'm sure someone wrote a crate to deal with them in Rust. Never use them. If your numbers get too small, write your own floating point library is my recommendation. Something to take away from all of this is that representation is not uniform between numbers. We have our most precision when we are very close to like 0 or 1. Numbers that you encounter in real life. Right? It was designed to do this. In a way, the designers of the floating point standard looked at all of the numbers they saw in scientific literature and made all of those representable. They did not look at all of the numbers that existed and made those representable. And because you a lot of times see 1.999567, you can store that number. And because you very rarely see 1,000,000,99967, you cannot store that number. And I totally made that up, but I bet it's true. How many zeros are on a trillion?
Well,
That's allowed, apparently. From numpy import float 32 as f32. Will we be able to do this with f32s? Maybe? No. Okay, so the floating point designers looked at this number. They said, I've never seen that in a paper. Therefore, it doesn't exist. It is relatively close to the other number. Note that did not round up. Right? That's truncating. Perhaps this should be interesting to us. Right? That's also going down. Okay, so it's truncating a lot of things. I wonder how... Yeah, they say, I've never seen 1,110,000,000. That's a completely fake number. I always use the example of, like, if you ask me the population of Portland, I can tell you that it's either 0.5, 0.6, 0.7, 0.8, or 0.9 million. And I cannot get more precise than that. I have less than 1 bit of precision, right? Or I have less than 1 digit of precision. I have a few bits, right? So look out for that. Here's a fun little graphic. I was going to ask you to make this, and I couldn't find a plotting library I liked in Rust. This person's a .NET developer. In the, like, there was a middle period at Microsoft where everyone there blogged for some reason. This should be interesting because this is the exact same style as on the Wikipedia page that does not cite this person. So there's some root source somewhere where everyone is making these same types of graphics to describe floating point, and I don't know what graphics library they used for this. I don't know how to generate something that looks exactly like this, and everyone was doing it at the same time years ago. So that's like just a historically interesting thing, right?
maybe they just all made their own library.
Maybe they all made their own library. I don't know. Right, so this, like, the code to make this had to be written in something that the Microsoft people are allowed to use in, like, 2005. I don't know what graphics library this is. It looks great to me, right? But the takeaway from this is we have a lot of precision close to 0 because we have a lot of numbers that aren't spreading out that far, right? This is basically I guess I'd call this a sigmoid. That's probably not what it is. Is this a hyperbola? There's some kind of shape, right? Gets exponential down, exponential up, but very close to flat at 0. The other thing to point out is this looks like a curve. This is not a curve. This is a piecewise function, okay? And it is piecewise in the following sense. These colors represent what the exponent value is, and numbers are linearly distributed within an exponent, and then they are exponentially distributed across exponents, right? So this is a series of line segments that are approximating this exponential curve. And that is the distribution of the floating point numbers. What this means is that there are highly irregular numbers of floating point values between different values. So from 0 to 0.1, there is 1 billion floating point values. And then from 0.1 to 0.2, there is 8 million. So if you are between 0 and 0.1, you are cruising. You're living the dream. The vibes are impeccable, right? And then you go from 0.99 or 0.099 to 1.01, and your life's over. Like, you've peaked. There's no longer anything here for you. And it continues falling off. So this looks linear and even, right? Oh, I tricked you because I'm in exponential scale over here. So 0.2, this is a distance of 0.1, then 0.2, then 0.4, then 0.8, then 1.6, right? So you get way less precision as soon as you're moving away from the 0.1 range. Why is that? Because a lot of scientific papers, they talk about ratios and percentages of things, and there's a duplicated pi. Look at that. That's tau. That should be 6.28. The problem that I posed at the beginning of class is, can we put pi in a computer? And the answer is no. From NumPy, import pi. There it is. How do I actually want to print that out? Give me as many digits as I can. That's NumPy pi. And this is, I asked Wolfram Alpha for an approximation of pi, and it gave me this enormous number. I should show you. Wolfram Alpha pi? Wait, what is... How does the internet work? I think we're blaming JavaScript for those ones. Should we blame? I think that's a JavaScript angle. Give me some more digits. Okay. And then I think I can just copy paste this probably somehow. Does anyone know how Wolfram Alpha works? Oh gosh. Plain text. Copy plain text. Okay. We will notice these numbers don't quite line up. 3.141592653589793. Okay, I learned there was a 2 here at this one, and we see that in fact is true. 3.141592653589793. 897932. Yep. So we start differing at this point on these two values, and there is a lot of pi left to go, right? Presumably all of these numbers are correct. I don't know them. Does anyone know more than like 30 digits of pi or something? Okay. Like when I was in middle school, the cool thing to do was to memorize digits of pi. And it was like, I memorized the second most after the person that got the math PhD. So I'm like, I always kind of feel bad about myself. That person got to 100. It was really cool. It was a party trick. Like we would all hang out after school reciting digits of pi to each other. I would like to reiterate I'm normal. Okay, I feel like I kind of buried that lead there. Okay. The way to measure precision in floating point values is units in last place. There is not a widely agreed upon way to measure units in last place. This is one. The spacing between two consecutive floating point values relative to the least significant digit. We can calculate this. This is this code is translated from Haskell. This is a single line in Haskell. It is more than one line in Python. It's very cool. Function F11. Okay. No, I'm not going to make you sit through me writing an intertools expression. See you Wednesday. Wednesday, you're going to implement your own floating point 16 values. We actually didn't get to the parts of the slides that are cursed. Because it gets really bad. Wait, this all looks fine. Is this actually fine?
Did you secretly push and slot it in?
This kind of looks like I fixed it. I'll figure it out someday.